19th of April, 1943, 7:45 in the evening, Vickers Armstrong Aircraft Works, Weybridge, England. Engineer Barnes Wallis stood beside a narrow test tank that stretched across the concrete floor of the laboratory. The tank was only a few yards long, but the problem inside it involved hundreds of thousands of tons of water. Wallis was not a bomb designer by training. He was an aeronautical engineer working for Vickers Armstrongs, known for structural aircraft design and geodesic airframes. Yet by 1943, he had become obsessed with a very different target: the dams of the German Ruhr industrial region. Three structures in particular dominated the landscape of Western Germany: the Möhne Dam, the Eder Dam, and the Sorpe Dam. These reservoirs powered turbines that supplied electricity to steel mills, chemical plants, and munitions factories across the Ruhr Valley. Without that power, German heavy industry would stall. Without the water supply, factories would shut down completely. British intelligence estimated that breaching the Möhne Reservoir alone could release more than 130 million tons of water into the Ruhr Basin. It would flood rail lines, collapse bridges, and halt production in some of the most important industrial plants in Europe. But there was a problem. German engineers had already prepared for aerial bombing. Massive torpedo nets hung in the water near each dam wall. Anti-aircraft guns surrounded the reservoirs. Standard bombs dropped from altitude could not guarantee the precision needed to break the concrete. The Möhne Dam itself was nearly 130 feet high and more than 600 feet wide at the crest. At the base, the wall thickness reached nearly 112 feet of reinforced concrete. Destroying it required an explosive charge placed directly against the dam face underwater, not near the dam, against it. Traditional torpedoes could deliver such a charge, but the torpedo nets blocked them. Bombs dropped from altitude would detonate on the surface or sink too far away. By early 1943, the problem appeared impossible. Wallis believed the answer came from an observation made during childhood. He had watched flat stones skip across a pond. If a bomb could bounce across the water surface, it could jump over the torpedo nets. If it continued forward, it could strike the dam wall directly. Then it could sink and explode underwater, where the pressure wave would hammer the concrete. In theory, the water itself would amplify the blast. But theory was not enough. Throughout early 1943, Wallis conducted dozens of small-scale tests inside the Weybridge tank facility. Steel spheres and cylindrical models were spun rapidly before striking the water surface. The spin proved essential. Without spin, the object skipped only once or twice before sinking. With strong backspin, the object bounced forward repeatedly while staying stable on the water. Wallis calculated that a full-scale weapon would need several precise conditions. The bomb must be released at exactly 60 feet above the water. Aircraft speed must be approximately 220 miles per hour. The bomb must rotate backward at roughly 500 revolutions per minute. If any of those numbers changed, the bomb would sink prematurely or skip wildly off course. The aircraft required for such a mission already existed: the 4-engine Avro Lancaster heavy bomber. Its large bomb bay could carry a cylindrical explosive nearly 5 tons in weight. But even the Lancaster required modification. The bomb would hang partially exposed beneath the fuselage. A hydraulic motor system would spin the weapon before release. 2 angled spotlights mounted beneath the aircraft would help the crew maintain exactly 60 feet above the water surface at night. The aircraft unit chosen to fly the mission would be newly formed. The Royal Air Force assigned the task to 617 Squadron Royal Air Force. The squadron commander was Guy Gibson, a highly experienced bomber pilot with more than 170 combat missions. Training began in March 1943. Lancaster crews practiced low-altitude flight across reservoirs and lakes in England. Many runs occurred at less than 100 feet above the water. Navigation errors of even a few seconds could mean disaster. Hills surrounded several of the German dams. Night fighters patrolled the region. Flak batteries guarded the valleys. The final weapon weighed roughly 9,000 pounds and carried about 6,600 pounds of Torpex explosive. Official designation, upkeep. But the crews simply called it the bouncing bomb. During early tests at Chesil Beach, several prototypes skipped successfully across the water surface before detonating near a test structure. Observers reported towering columns of spray rising hundreds of feet into the air. The concept worked, but success in testing did not guarantee success in combat. To reach the Ruhr dams, the Lancaster crews would need to fly more than 300 miles across heavily defended German territory. Most of the journey would be flown at less than 100 feet altitude to avoid radar detection. If even one aircraft misjudged the final attack run, the bomb could strike the dam crest instead of the water. If the weapon skipped too far, it would explode harmlessly beyond the wall, and if the attack failed entirely, the months of engineering effort would mean nothing. By early May 1943, the operation received its official name, Operation Chastise. The mission date approached rapidly, but one final problem remained. The aircraft crews had never attempted a real combat drop against a full-scale dam, and the German defenses around the Möhne Reservoir were growing stronger every week. The success of the entire plan depended on a few seconds of perfect flying in darkness. Seconds that no engineer could control once the aircraft crossed the German border. The test tanks in Weybridge were silent now. The calculations were finished. Soon the mission would leave England, and the real test would begin. 16th of May, 1943, 9:28 in the evening, Royal Air Force, Scampton, Lincolnshire, England. The runway lights remained dim as ground crews prepared 19 modified Avro Lancaster bombers along the dispersal area. Each aircraft carried the same unusual weapon, the cylindrical upkeep bomb designed by Barnes-Wallis. The crews of 617 Squadron Royal Air Force had spent nearly 2 months preparing for this night. Their commander, Guy Gibson, gathered the pilots for a final briefing shortly after 8:30 in the evening. Maps of Western Germany covered the wall. 3 primary targets were marked in red pencil: the Möhne Dam, the Eder Dam, and the Sorpe Dam. The operational objective was simple in wording but extremely difficult in practice. Destroy the dams, release the water stored behind them, shut down industrial production in the Ruhr Valley. British intelligence believed that if both the Möhne and Eder reservoirs were breached simultaneously, massive flooding could spread across more than 50 miles of river valleys. Steel production would fall, electrical power stations would stop, railway networks could collapse under the sudden surge of water. The map of industrial Germany might change overnight, but reaching those dams required precision navigation across hostile territory. The squadron was divided into 3 separate attack waves. The first formation contained 9 Lancaster bombers led by Wing Commander Gibson. Their destination was the Möhne Dam. The second wave of 5 aircraft would attack the Eder Dam if the first group succeeded. A third reserve formation of 5 bombers would attempt the Sorpe Dam or reinforce earlier attacks if necessary. Each aircraft carried a crew of 7: pilot, flight engineer, navigator, bomb aimer, wireless operator, mid-upper gunner, rear gunner. The Lancaster crews had practiced low-altitude flight across British lakes for weeks. Many practice runs occurred at less than 100 feet above the water surface. But tonight the mission required even greater precision. The bomb release point had to occur exactly 60 feet above the reservoir. Aircraft speed had to remain close to 220 miles per hour. If the speed dropped too low, the bomb would sink prematurely. If the aircraft flew too high, the bomb would bounce unpredictably. To help the pilots maintain the correct altitude, 2 angled spotlights were mounted beneath the aircraft fuselage. When the beams converged into a single point on the water surface, the aircraft was exactly 60 feet above the reservoir. Distance to the dam was measured with a triangular wooden sight held by the bomb aimer. When the 2 towers on the dam wall aligned with the sight marks, the bomb aimer released the weapon. It was an unusual combination of precision engineering and improvised wartime tools. At 9:39 in the evening, the first Lancaster began rolling down the runway. The second aircraft followed 1 minute later. Within 30 minutes, all 19 bombers were airborne and heading southeast across the North Sea. The flight path crossed the Dutch coastline near the island defenses of Walcheren Island. German radar installations along the coast were capable of detecting high-altitude bomber formations, but the Lancaster crews flew extremely low. Many aircraft remained below 100 feet above the water. At that altitude, radar detection became difficult, but the danger shifted to another threat: high-tension power cables, church towers, windmills, navigation errors in darkness. At 11:15 in the evening, the first losses occurred. 1 Lancaster struck high-voltage power lines near the Dutch village of Ries. The aircraft crashed into farmland and exploded. Another bomber encountered heavy anti-aircraft fire near the coastal defenses of the IJsselmeer. German flak batteries opened fire as the low-flying bomber crossed the water. The Lancaster was hit repeatedly and fell into the sea. Even before reaching Germany, 2 aircraft were gone. The surviving bombers continued eastward. At 11:56 in the evening, the first formation reached the valley of the Möhne Reservoir. The dam appeared suddenly in the darkness, a massive concrete wall stretching across the valley floor. German anti-aircraft batteries opened fire immediately. Searchlights swept across the water. Tracer rounds streaked upward from gun positions along the shoreline. Wing Commander Gibson made the first attack run. His Lancaster descended to exactly 60 feet above the reservoir. The aircraft raced toward the dam at 220 miles per hour. The bomb beneath the fuselage spun backward at 500 revolutions per minute. The spotlights merged on the water. The towers aligned in the bomb sight. Release. The upkeep bomb struck the water and skipped forward across the reservoir. 1 bounce, 2 bounces, 3. Then the weapon struck the dam wall and disappeared beneath the surface. A few seconds later, a towering column of water erupted beside the concrete structure, but the dam still stood. Gibson circled the reservoir and drew German anti-aircraft fire away from the next approaching Lancaster. 1 by 1, the bombers repeated the attack run. Each aircraft flew through a wall of flak to reach the release point. Some bombs detonated too far from the wall. Others struck the dam but failed to cause visible damage. Then shortly after 12:40 in the morning on 17th of May, 1943, the 5th attack aircraft released its weapon. The bomb skipped across the reservoir, struck the wall, and detonated underwater against the base of the dam. Observers aboard the circling aircraft watched carefully. At first, nothing happened. Then a thin crack appeared in the center of the concrete wall. The crack widened. Water began to pour through the opening. Within seconds, the pressure behind the reservoir forced the breach wider and wider. The Muna Dam was beginning to fail. But the night was far from over. Another dam still waited in a different valley, and the next target would prove far more difficult to attack. 17th of May, 1943, 12:48 in the morning. Muna Valley, Western Germany. The concrete center of the Muna Dam finally gave way. A section nearly 250 feet wide collapsed under the pressure of the reservoir behind it. Within seconds, a wall of water surged through the breach. More than 130 million tons of reservoir water began rushing down the narrow Muna Valley. Observers aboard the circling Avro Lancaster bombers watched the dark flood spread through the valley below. Railway bridges vanished beneath the surge. Trees and farm buildings disappeared in the rising current. The operational objective of Operation Chastise had been partially achieved, but the mission plan required more than one dam. Destroying only the Muna reservoir would cause severe flooding, but German industry could still recover if other water supplies remained intact. The next target lay roughly 40 miles to the south, the Eder Dam. Unlike the Muna Dam, the Eder reservoir sat inside a winding valley surrounded by steep hills. Approaching aircraft could not fly straight toward the wall. Each Lancaster had to descend into the valley, follow a sharp turn along the water, and align with the dam in darkness. This maneuver left very little time to stabilize the aircraft before the bomb release. Shortly after 1:20 in the morning, the first Lancaster from the 2nd Attack Group reached the Eder Valley. The pilot attempted an approach, but aborted the run. The valley walls forced the aircraft dangerously close to the hillsides. A second bomber attempted the same approach minutes later. The pilot also aborted. The Lancaster climbed away from the reservoir and circled for another attempt. Inside the aircraft, the bomb aimer checked the triangular sight used to judge distance from the dam towers. The two angled spotlights beneath the fuselage illuminated the surface of the reservoir. The pilot needed the two light beams to merge into one point. Only then would the aircraft be exactly 60 feet above the water. After several attempts, Flight Lieutenant Leslie Knight finally completed the approach. His Lancaster dropped into the valley and leveled out over the dark surface of the reservoir. Speed increased to approximately 220 miles per hour. The spinning upkeep bomb rotated beneath the aircraft. Knight held the Lancaster steady as the dam wall rushed toward the cockpit. The spotlights merged. The towers aligned in the sight. Release. The cylindrical bomb struck the water and bounced toward the wall. One skip, two, three. Then the weapon struck the dam face and sank beside the concrete structure. Moments later, a deep underwater explosion lifted a column of spray into the night air, but the dam still held. Two more Lancaster crews attempted the same dangerous approach. Their bombs detonated near the base of the wall but failed to cause visible damage. Finally, during another attack run by the crew of Flight Lieutenant Knight, a properly placed detonation struck the foundation of the dam. The explosion hammered the concrete with enormous hydraulic pressure. Observers watched carefully from the circling aircraft. At first, the structure appeared unchanged. Then a section near the center of the wall began to crumble. Cracks spread outward along the masonry surface. Within seconds, the reservoir pressure forced a large section of the dam to collapse. Water burst through the gap and poured into the Eder Valley below. The second major objective of the mission had now been achieved, but the final target remained: the Sorpe Dam. Unlike the other two structures, Sorpe was an earth-filled embankment dam rather than a solid concrete wall. This design absorbed blast pressure more effectively. A bouncing bomb striking the upstream slope might not create the same catastrophic breach. Nevertheless, two remaining Lancaster aircraft attempted attacks shortly after 2:30 in the morning. Instead of skipping the bomb across the water, the crews released their weapons directly along the crest of the dam. The explosions damaged sections of the structure but failed to produce a full breach. By 3:15 in the morning, the surviving aircraft began the long return flight toward England. The journey home proved just as dangerous as the outbound route. German night fighters and flak batteries remained active across northern Europe. Several damaged bombers struggled to remain airborne as they crossed the Dutch coastline. Of the 19 Lancaster aircraft that departed Royal Air Force Scampton earlier that night, 8 failed to return. 53 aircrew members were killed during the mission. Despite those losses, the strategic effects inside Germany were immediate. The collapse of the Muna and Eder dams released enormous floodwaters across the Ruhr Basin. Dozens of bridges and rail lines were destroyed. Electrical power stations along the river valleys shut down. Factories dependent on reservoir water halted production. German authorities diverted thousands of workers and engineers to emergency repairs across the region. Industrial disruption lasted for several months. However, the long-term effect proved more limited than British planners originally expected. German engineers rapidly constructed temporary dams and restored much of the damaged infrastructure within the same year. Yet the operation achieved something beyond physical destruction. It demonstrated that carefully engineered weapons combined with precise flying could strike targets once considered impossible to attack. The unusual bomb, designed by Barnes-Wallis, had turned a theoretical idea into a real battlefield result. A weapon designed by studying how a stone skipped across water had breached two of the most heavily protected dams in Europe. The success of the raid also established the reputation of No. 617 Squadron Royal Air Force, which later became known for specialized precision bombing missions throughout the remainder of the war. But on that early morning in May 1943, the crews returning to England were not thinking about future operations. They were thinking about the empty aircraft seats beside them, and the quiet reservoirs now draining through the valleys of western Germany.